Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello everyone, welcome to the session. So it's a great pleasure to introduce Stephanie. Stephanie is a faculty member at MIT. Before that, she was doing postdoc at Berkeley with Michael Jordan, and before that she finished a PhD from MPI with Jeff Bimes. Stephanie is known to be a leading expert on submodular functions and their optimization, and she has done amazing work in last few years on that. And we are really excited to that she's talking about submodular functions here. Over to Stephanie.
Thank you. So yeah, from my side also welcome back to this session. In the next two lectures we will slightly switch gears in that we will now talk about some combinatorial problems and subset selection problems. You will see it's actually not completely different because we will see some of the convex optimization methods that you just learned about reoccur in the combinatorial setting as well. So there are many things I could talk about regarding submodular functions. I chose to talk mostly about optimization aspects of those because those might be most immediately useful to you. So what are we actually going to talk about here? So first of all, we are going to talk about set functions. That means in all cases we will have what we call a ground set of elements. So here are some elements and we could choose a subset of these elements. So here we could choose like some food and some drinks for lunch later on. And we will have a function f, which is a set function. That means it will give us a score for any subset that we pick. So it's defined on all possible subsets. And this function could be a lot of different things. It could be the cost of buying these items. It could be the utility, that how much we like these items. It could be a probability of these items occurring together, and so on and so on. So we will see this in different contexts. We will make two small assumptions. The first one is that f evaluated at the empty set is 0, which is not so much of a big assumption when you do optimization because all this is it's shifting your function by a constant if this doesn't hold. The second thing is that I will not really talk much about how we actually evaluate the function. So I'll show you some examples of the functions. It'll be clear that you can actually evaluate them. In some cases, you might only be able to evaluate them noisily. That's usually also fine. You can generalize to that. So mostly I will just say, okay, we have some kind of subroutine that computes f. So where do these kinds of subset selection problems occur when we actually do machine learning or data analysis? This is obviously a very different real-world problem, but maybe not what we care about in machine learning. So let me just show you some examples. So one example is discrete labeling problems, where you could say, well, this is a subset selection problem in that I select a set of variables that take a certain label. So this is very important in computer vision, for example, where I want to label the pixels in an image. It also occurs in computer vision in other settings where we say have a bunch of images and we want to extract the objects that are common to a set of images. This is called co-segmentation. There are other settings, for example, summarization. So let's say I have a large collection of documents or videos or images and I would like to summarize them. I don't want to look at all of it, so but I would like maybe to extract some sentences from my documents that summarize the content adequately. So in this case, my scoring function would maybe model something like a relevance or the non-redundancy of the subset that I selected. And similar things hold for ranking or web search. What I would like to return is a set that somehow captures most of the stuff that I found, but is not so redundant. There are many other problems where similar things occur. So for example, all sorts of different sensing problems where I would like to find informative subsets of some sort. So place your sensors somewhere to gather as much information as possible, do summarization or do experimental design. And just figure out essentially which kinds of experiments should I run to get the most information, or which kinds of points should I get user labels on to get the most information from a learning problem. Other kinds of subset selection problems you have seen, I think you have seen a little bit about sparse problems. So essentially you could view sparsity as selecting a set of coordinates where my vector is non-zero. So if you don't remember, the setting is usually you have, for example, a regression or a reconstruction problem. You observe a noisy signal, and you would like to reconstruct, say, that image. And you can reconstruct this by finding a combination of certain basis vectors that represents that image well. So essentially, you know that the true representation is sparse, and you're using this. So essentially, you're just trying to find the correct basis vectors here, very, very broadly. And of course, you have to find the correct weights. So we see there's a lot of different subset selection problems actually occurring. The question is, how could we solve them? Like, we'll have our scoring function, and that scoring function, we want to optimize that. That's the subset selection problem. So all the problems I showed you here have a specific structure, which is called the structure of submodularity. And as we will see, this is actually very useful, because if you think about it, in general, having any kind of scoring function and not knowing anything else about the function, this problem of optimizing that a set function is really, really hard. It's just a combinatorial search problem, essentially. Try all possible subsets, and that's it. So there's not much we can do. If we have some more structure, if we know some properties of our scoring function or probability, etc., we can maybe do better. And this is will be the structure of submodularity. I'll first spend some time just showing you more examples of submodular functions, defining what is a submodular function. And then I will go on and go to optimization. What will be important here is the relation of submodularity to convexity. So the property of submodularity is also called a discrete analog of convexity, and we will see why. And later in the afternoon, I will also tell you more about how to maximize submodular functions. So you have both ways. And the techniques are somewhat different. So what is a submodular function? So just as a running example, let's go back to sensing problems. So let's just say I have a room or some other space that I would like to observe. And I would like to place sensors somewhere. So the ground set of elements in this case is all possible locations where I could place sensors. And I would like to place them so as to, for example, detect the temperature change as quickly as possible to, say, detect a fire outbreak. And in that case, my set function measures the information gained from the locations where we placed our sensors. So what will be important in defining this property of our functions will be what we call the marginal gain or the marginal cost. So what is the marginal gain? It's essentially just, let's say we have picked a subset A. The marginal gain of an additional element S is simply how much does my function increase when I add S to my set. So in this particular case, we just look at, okay, how much information do we have from these two sensors, which is the set A? How much additional information do we get from the new sensor S? So now, the property of submodularity is the same as diminishing marginal gains. Let me try to elaborate on that a bit more. So let's say we have two different subsets. First is placement A, and placement B is the same as A with some stuff added. So B is a superset of A. Now we look at the marginal gains of adding another sensor to these two configurations. So let's add another sensor. If we add it to the smaller set A, we actually get a lot of more information because we are sensing a whole lot of new area that we haven't looked at before. If we add the same sensor in the same location to the set B, we don't actually gain so much more because we basically know everything already. So what does this mean? That in general is that we have two sets. A is a subset of B, any two sets. And we look at how much do we gain from adding an additional element to that. And if we add the element to the smaller set, we always gain more than if we add it to the larger set. Or in other words, the more we have already picked, the smaller is the marginal gain of any additional thing that we add. So that's the property of diminishing gains. We could look at the same thing in terms of cost functions. So it's the same thing. Just another example, let's look back at our food example. Let's say we have to buy food, so we have already chosen the fries, and we add a drink to it. The additional cost that we get is just the cost of that drink. However, if we have already chosen a drink and what we get is a free refill, all the other drinks come for free. So in that case, we also have diminishing marginal, in that case, costs. So the additional cost of adding the drink S in this case is 0, because we've paid for all drinks that we'll get. In this particular case, where the set function is a cost function, what submodularity models is something like diminishing costs, or diminishing marginal costs. So essentially, our function increases as a concave function. So this is important in economics, for example, the game theory, and so on. So we have this definition of a submodular function via the marginal gains. There's an alternative definition via union and intersection. So above, we always assume that A is a subset of B, and we just looked at the marginal gains. Equivalently, we can look at any two sets S and T, and we measure our function on S and T, and then on the union and the intersection. And these two definitions are equivalent. So the function is submodular if and only if this holds for all subsets S and T, or this holds for all sets where A is a subset of B. And you can see that these are equivalent if you do a little bit of a mapping, that you map A union E to S and B to T, and then you just rearrange a little bit. You will see that these are, so you can prove that these are actually the same. So why am I showing you these two? Well, in some cases, showing submodularity is easier with one than the other. So it's good to have these two different definitions. Mostly, I think that the upper one is more intuitive, but it's good to have both of them. So before we actually get into the details, I just wanted to say a little bit about the history of studying submodular functions. Of course, submodular functions have not been invented with machine learning. In fact, the study of submodular functions is older. It goes back to people like Choquet and Edmonds and Shapley, coming from different directions. So Jack Edmonds looked at submodular functions based on the theory of matroids, if you know what a matroid is. If not, it doesn't matter. Shapley looked at them from the perspective of game theory. He wrote a paper on the course of convex games where he essentially described some of the polytopes that we'll look at later on. Edmonds did the same thing from a different perspective. Lovasz later on, a few years later, used these results to define more closer relations between submodularity and convexity. And moreover, submodular functions come up in many, many different areas, not only machine learning. It's useful to know about that there's a lot of different areas. If you look at different submodular functions and look at different results and perspectives, that can be helpful. So overall, it's a pretty broad concept. So let's just, to get started, look at a few more examples and look at what does the concept of submodularity actually mean, where does it come up, and so on, before we go into some optimization. So the first function, which is maybe the simplest, as simple as it can get, is the following, that each element in our ground set has a weight, and the cost function or the gain function is just the sum of these weights. So essentially, it's a linear function. If we think about the definition of submodularity, the marginal gain or the marginal cost of the element E is always the weight of E. The function always increases as the weight of E. No matter what the set A or B or something is, it's a sum, so the marginal gain is always the same. In that case, our submodularity inequality holds with equality, always. So linear functions, which are also called modular functions, are always submodular. And here you also see where does the name submodular come from. Modular is like a linear function. A submodular function is sort of like the decreasing gains version of that. So it's always below the linear function. So this we can just keep in mind. Linear is always submodular. Let's look at something more interesting and go back to our sensing example. So how could we actually model this problem? And the super simple way of modeling this is just say, well, for each location where I place a sensor, I gain the area that the sensor covers in some sense. So in that case, our gain function would be a coverage function. That we look at all the locations that we pick, and we just take the joint area that they cover. So now if we look at the marginal gains, let's say we have picked the blue location and we add the green one, we get the full additional disk. But if we have already chosen the blue, a lot of blue ones, the additional gain is much smaller. So we see proof by picture that coverage functions are actually also submodular functions. Now maybe coverage is a very simplistic model of the sensing problem. We can do slightly better than that. So let's, for example, set up a probabilistic model, a graphical model in this case. So we have our hidden temperatures y, which are unknown, and what we can observe is the temperatures x, which is y plus some noise. Now we would like to pick locations, essentially a subset of the x variables, that give us as much information about y as possible. So the way we can set this up is simply we look at the joint probability of these. And then the utility of having sensors at certain locations is essentially how much does my uncertainty about y decrease as I add more measurements. So for example, we can just look at how much does the entropy decrease, which is the same as the mutual information between y and my variables x that I observe. So I just try to maximize that in that case. Now, this turns out to be a submodular function under slightly more conditions. What we need is that the x variables are conditionally independent given the y's. So I leave the full proof to you as an exercise. It essentially relies on the modularity and on the other following thing, that the discrete entropy function is a submodular function. So what do I mean by this? Let's say we have n discrete random variables, x1 to xn, and our function f of s is the joint entropy of the variables indexed by s. So now what is the marginal gain in this case? Let's just look at that. We have the marginal gain of A union E, of E given A. And this is nothing else than the conditional entropy of the variable xe given the variables in A. So now we know that if we condition on more and more variables, actually the entropy can never increase. It can only decrease. Essentially, information never hurts us. So what this means is that we get diminishing marginal gains. So that proves that entropy is a submodular function. Now, entropy gives us another interesting connection of submodular functions. If we think of the following: if your variables are actually statistically independent, what does the entropy look like? In that case, essentially, the entropy is just the sum of the entropies of the single variables. If they are dependent, this is not the case. If they are independent, this is always the case. So this means that from the properties of my submodular functions, I can actually infer something about the independence of these variables. Similar things hold for linearly independence of vectors and many other combinatorial notions of dependence. So let's now say that, well, my ground set of elements is just a bunch of vectors, and I'm choosing a subset of vectors, and my function will be the rank of the matrix formed by these vectors. If these vectors are linearly independent, the rank will be the same as the numbers of vectors. If they are linearly dependent, then it'll be smaller than that. So in this case, this rank function also shows us independence, essentially. It's modular if the elements are independent. And this rank function and many other generalized versions of rank functions are also submodular functions. Now, there are a few other examples. For example, diffusion in networks. So let's say we have a social network. I am infecting or informing a few nodes in this network, and I look at how information propagates in this network. So I have some kind of stochastic process that, like, how these are propagating. And one can show that essentially it's very similar to the coverage example, that the more I have nodes I have already infected, the less essentially I gain from adding an additional node. And in that case, the set function is the expected number of nodes after infecting the nodes in the set S. And under certain, like several different diffusion models, this is also a submodular function. So graphs have many different interesting functions. Another function is graph cuts. So what about a graph cut function? The function you probably know is that I pick a subset of the nodes, and the cost function in this case is the summed weight of the edges that I have to cut to extract these nodes from the graph, cut them out. So let's look at the simplest graph cut function, which is a single edge, and let's see if this is a submodular function. So we look at, in this case, the other definition of submodularity, just to practice a little bit about the definition of submodularity. So I just look at the set S and T, which is in this case U or V, the single nodes, and then I look at the union and the intersection, which is empty. So if I take any single node, I have to cut the edge, so I pay the weight of that edge. If I take them together, I don't cut any edge, so I have cost 0, and if I take the empty set, I define this to be 0. So in this case, we see that if the weights are non-negative, the function is actually a submodular function. And then what's a cut for a larger graph? It's essentially the sum of the cut functions for the single edges in the graph. And if you think about it a bit, it's not hard to show that submodularity is closed under summation. So if I take a sum of submodular functions, this will still be a submodular function. So we've seen a bunch of combinatorial examples. I would like to make one more connection and show you two probabilistic models with submodularity in it. So one important connection that we'll encounter throughout these lectures is the following, that instead of looking at a ground set here of 4 elements, I can look at Boolean vectors or binary vectors, which are essentially, for each element in my ground set, I have an entry in my vector, and then the vector is just the indicator function of the set. Just the indicator of the set. It's pretty easy. It's a direct connection, so instead of looking at the set function, I could look at a function on binary vectors. These are interchangeable. Where do these functions come up? One of them is in very classical problems in computer vision. So let's say I have this image, and I observe the pixels in this image, and what I would like is to extract the object from the image. So I set up a model which tells me what's the probability of, so for each label, pixel, I have a label now, a hidden label that I don't know. And my model tells me what's the probability of the labelings of all the pixels given the images that I observe, the pixels that I observe. This is usually phrased with a so-called energy function in there. And now, if I want to maximize the probability, do map inference, essentially just find the labeling that maximizes this posterior probability. I have to minimize that energy function. So now what properties will this energy function have? Let's think about this for a little bit. I could essentially set up a very simple model and say each pixel by itself has an independent label. And now I have some kind of model that foreground has maybe always red and background has some grayish colors. And essentially what this does is it classifies each of the pixels by its colors. So I have some kind of generative model like this. This is, if I do this, and now I infer the best labeling, it looks something like this. So it kind of goes by colors, but the segmentation that I get of this image is very, very noisy. But of course, an image or an object in the real world is not really like this. It has much more structure to it. For example, it has spatial coherence. So 2 pixels that are next to each other are much more likely to have the same label than different labels, especially if they look very similar. So what I can do then is to introduce dependencies between my hidden labels. And that is expressed via pairwise terms of my energy function. So now what will these look like? Well, I already said this. Okay, this is something messed up. What essentially I want is that if my pixels take different labels, which is here 0, 1, and 1, 0, the energy should be higher. That means the probability is lower than if they take the same label. Now, what does this all have to do with submodularity? I can now go back from my binary labeling problem to my subset selection problem and just say, well, if I have these 2 different nodes, and I have these two different entries in my vector. I have elements I and j, and I define set S to be I and set T to be j. What this spatial coherence, also called attractive potential, really means is the same as submodularity of my pairwise functions. And now I have a sum of these, so the full energy function in this case is a submodular function as well. Now what these submodular functions model essentially is that a preference that lots of different things occur together or pixels take the same label. I could try to do the opposite, and that is introducing priors for diversity. Let's take another example from computer vision. Let's say I have this image with people in them. I would like to recognize the people, or just like estimate where are actually the people. So I want some kind of probability of my set of people that are actually occurring given the data that I observe, which is the image. So for that, I introduce a prior on the set of possible people that could occur, and then I just take the likelihood here. So now what prior would I have? Well, the prior that I have in this case is that people are somehow disjoint. They cannot stand exactly in the same place, so people somehow have to be spread out in my scene, so somewhat. So I want something that is like more like a repulsive thing, that people don't actually occur on top of each other, but farther away. So how can I model this? There's other models that model this kind of repulsion or spread across space as a prior. And one of these is called determinantal point processes. I'll just give you the idea of what these are. I think there's a lecture later in the summer school that might refer back to things like this. So how do I set these up? Essentially, I have a similarity matrix between my elements, and now what I want is a probability that is small if my set contains lots of similar elements, and it's large if it contains lots of dissimilar elements, which means my people are spread out in the scene in this case. So in this case, the probability is defined by the determinant of a submatrix. So I have my similarity matrix, which is in this case normalized, and each element corresponds to one row and one column, and this is a symmetric matrix. And the probability of observing a set S is proportional, or it is the determinant of that particular submatrix. So why does this model this kind of repulsive property? Well, we can think about it. Let's just look at the probability of a certain element E occurring in a Y. That's just the diagonal element. It's like a 1-by-1 matrix. Okay, that's easy. What's the probability of two elements occurring together? That probability is the determinant of a 2-by-2 matrix, and that's the probabilities of these two guys. If they were independent, we would just have the product of these two. But in this case, minus Kij, which is the similarity of the i's and the j's element. So the more similar they are, the smaller is the probability that they actually occur together. So that's just the intuitive argument why this models repulsion. Now, this function the log of this probability is also a submodular function. So that's why I'm showing you this. So submodular functions help us set up these attractive potentials as well as these repulsive properties. So what does this actually mean here with the diversity priors? What I'm seeing here is the probability of all sorts of things occurring without having chosen anything. Here is the conditional probability given that I say I have decided that there's a person in this location. What's the probability of locations for the remaining people? And you see, choosing this person sort of eliminated all the hypotheses here of where people are. What remains is stuff on this side, and so on. So now I've chosen 2, eliminating a lot of other things. Okay, so in summary, we saw, we've just gone through a bunch of many different examples of where all submodular functions occur. So they occur in combinatorial problems, they occur in information theoretic properties like entropy or mutual information, and they also occur in probabilistic models. over subsets and over discrete labels. So now let's see, okay, how could we compute with submodular functions? Let's look at some of the closeness properties of submodular functions. How could I create new submodular functions from functions that I have? We've already seen that the sum of submodular functions is submodular. Here are some more operations that I could do that preserve submodularity. The first one is that I have my ground set V, and I take a subset W, and even though I choose the set S, I really only measure the intersection of S and W for any set S. I just essentially restrict everything to the set W. That remains a submodular function. I can do conditioning, which means that I always merge with the set W instead of intersecting with it. That also remains a submodular function. So I basically always forcefully include that subset. Or I could do what's called a reflection, that instead of actually measuring S, I measure the complement of S. So if the complement function is submodular, this function is submodular, and vice versa. So this is just a few different things of how we can show that something is submodular, how we can design new functions. Now, as we go to optimization, and in general, it might be an interesting question, and it actually was discussed a lot. Are submodular functions more like convex functions or more like concave functions? And this is something to think about. So we have this discrete function. Does it look more like a discrete analog of convexity, which I said, or is it more like a discrete analog for concavity? And in some sense, it's both. So I'll show you there's actually arguments for either side, and which is also very useful for us because it will be handy for minimizing or maximizing those functions. So what we will see a lot in the remainder of these lectures is relations to convexity of submodular functions. So there are duality results that one can show, and this will lead to efficient minimization via something like a relaxation or an extension of that function. On the other hand, if you think about the definition of submodularity itself that I showed you, the diminishing marginal gains or costs, and if you think about the definition of concavity, which is that the gradients of my functions are decreasing, so decreasing slopes, that's pretty much the same thing. This diminishing returns basically means that the increase of my function degrades. It's becoming smaller and smaller. So in that sense, the function behaves like a concave function by that definition. And in fact, the connections are somewhat deeper than that. For example, we could define a set function as follows, that we take our set, we take the cardinality of that set, and then we just put this through a scalar function g. So we could define a set function for any such function g. And that set function that I define this way is submodular if and only if the function g is a concave function. So only that gives me my diminishing gains. So in that case, the function really looks like that. So now if we look at concave and convex functions, there is more actually about convex and concave functions. For example, taking a minimum of concave functions or a maximum of convex functions. If I take the minimum of concave functions, that preserves concavity. So what about a submodular function? I could define a function. I have two submodular functions. I take the element-wise min of these two functions. Does this preserve submodularity or not? So you can have a guess. Here's a picture. So let's remember the previous slide with these scalar functions which are concave. And sorry, I said like convex, maximum of convex function remains convex, not the other way around. So I take two submodular functions which are just a concave function of a cardinality, and I take their max, and that is not a concave function anymore of the cardinality. So submodularity is not closed under max. Unlike convex functions, this is not a submodular function in general. So what about the opposite then? Maybe that taking a minimum of submodular functions. If I have concave functions, the minimum of concave functions always remains a concave function. Maybe the other way holds, so they are more like concave functions actually. So let's look at an example. Here I have two submodular functions, f1 and f2, on two elements, and I take their min. And now I check the submodularity for this. So I use A and B as the and their intersection and union. And what I see is that submodularity does not hold. So submodular functions are neither closed in general under min nor under max. Only in special cases. So this is something to be careful about. Now we've seen a lot of stuff on like general submodularity. Now I think we have somewhat of an intuition. What does submodularity mean? Where all does it occur? Let's look at how can we actually do these solve these subset selection problems and actually do optimization of these set functions. And for that, we'll start with minimization, and for that, we'll start with relations of submodular functions to convex functions. We'll also talk a little bit about polyhedra and then about some of the convex optimization algorithms that you already saw. So for that, we'll again just recall our direct relation between set functions and functions on Boolean vectors. And always remember, when you see vectors, each entry in the vector corresponds to an element in my ground set. So what are we going to do? The idea is essentially, let's do a relaxation of our problem. So our submodular function is only defined on binary vectors. That means essentially only in certain points on the space, on some corners of a hypercube. What we want is we want a function that is defined everywhere. So that's somehow an interpolation of my set function, and then minimizing my set function is the same as solving this problem for a discrete vector x. Now we relax this for a continuous vector. And the hope is that the relaxation is good enough to give me some decent solution for this. So it's sort of like going from an integer program to a linear program, just that now we have a nonlinear function. So how do we do that? So let's think, how could we define an extension of this discrete set function? So we have f, we can evaluate f only on sets or only on binary vectors. And I have a vector x, and now I would like to evaluate some function on x which is close to f, and which evaluates to f if the vector is actually a discrete vector. Okay, so how could we do this? Well, one thing we can do is we can write our vector as a combination of indicator vectors. That is always possible, I can always do it, and there's a unique way of doing this. And then I can use that maybe. So how would I do this? I'll take my example vector x, and essentially I look at the elements in x and I order them. I look at the smallest value that x has. I take everything which is larger than my smallest value. That's everything. So I get the full indicator vector weighted by 0.2. Then I take the second smallest entry. I take everything that is larger. So essentially I take a threshold. I take everything that's larger than this threshold of 0.5, which is the top three elements. I get this set, this indicator vector, and so on. I take the next largest value, I get this one. And now what are the weights? The weights, I start with the smallest one is 0.2. Then for these guys, to reach from 0.2 to 0.5, I need this much, and so on and so on. So these are my weights alpha. So now what I have is I have a decomposition of my vector into sets. These sets are, you see, they're actually nested. So S1 is a subset of S2, S2 is a subset of S3, and so on. That's always the case. This can always be done, and it's unique. It's pretty simple to do, actually. So now what I have is I have indicator vectors, and now I can evaluate my function, so I can define my extension as follows. That I just take my indicator vectors and evaluate the function on those, and I take the same alphas. We did combination. So this is easy to compute. I hope you agree with that. This is the extension that we'll do. So let me just show you two examples of this extension. Here we have now only two elements to make life simple. For the example, we have 0.5 and 1. So now let's try to compute this extension for, say, this particular function. This is a submodular function. You can check it. It's very simple. It's 1 everywhere except for the empty set. So what does the extension of this function look like? This extension essentially in this case becomes 0.5 plus 0.5. And if you remember how we computed the values alpha, this will always be the maximum entry in my vector. So this is, if this vector is non-negative, is essentially the same as a maximum norm. Let's look at another example, the cut function on 2 elements, 2 vertices. What does it look like for this thing? So in this case, we get 0.5 times the full set, which is empty 0, plus the difference of the 2 entries times 1, which is the cut for a single element. And you can show that what comes out, if you think about it a little bit and play with it, what comes out will always be the absolute difference between these 2 entries. And if you look at a larger graph, this is also known as the total variation function. So these are just 2 examples of this extension. And there are many more, and you see that these examples actually do not look too unfamiliar. So some of these combinatorial functions actually have direct relations to convex functions that we are familiar with. Now this extension that I showed you, to actually make it useful for optimization, it should ideally have some other properties than just to be computable. Computability is already a good start. And this extension is also called the Lovasz extension, because Lovasz showed in 1983 that this extension is convex if and only if the set function is submodular. So far, if you think about it, I have actually not used submodularity at all. This kind of extension for a set function, I can compute it for any kind of set function, as long as I can evaluate f. So this thing is submodular if and only if, this thing is convex if and only if f is submodular. This you can maybe not directly see, but one way to see this more directly is because I can equivalently write the function as follows as a so-called support function. And I think you've seen support functions in the previous lectures. Basically, I can write this function as an optimization problem over some polytope. And now a polytope is just a collection of linear functions. So a maximum of linear functions is always convex. So this is a convex function, and in fact it's piecewise linear, and it looks exactly like this. So it's an interpolation, it's piecewise linear, and it's convex always. So what is now this BF in here? I said it's a polytope. Let's look what is this, because it's somewhat important actually for what's coming next. So what's the polytope? To define this polytope, we have to first define what's called the submodular polyhedron. So every submodular function has a polyhedron associated with it. And these polyhedra, they look kind of scary maybe the first time you see the definition. They actually have a very, very nice and very beneficial structure. And they are defined as follows, that I live in Rn. If you remember, I have vectors. Each entry in the vector corresponds to an element in my set. So I look at all the vectors, and I look at the vectors that are essentially dominated by my set function. So for each element subset, I have a constraint, and the constraint says that if I sum the elements in Y, which are indexed by a set A, then this should be smaller than f of A. So let's just take a simple example of a function of 2 elements. So I have 2 coordinate axes, ya and yb for a and b. Why is it? Okay, here's my function. Now, what do the constraints look like? Let's look at the first one. The first one says coordinate 1 should be smaller than -1. So I get a feasible region for my y's, which is everything, this blue space here, everything to the left. The second constraint says that the second coordinate should be smaller than 2. So I get the intersection of these 2 constraints. This is that feasible region here. Now the last constraint says that the sum of the entries A and B should be smaller or equal than 0. So this is my last constraint. So overall, I get a polytope that in 2 dimensions, it always looks something like that, somewhat shifted in different directions, but pretty much like that. So this polytope has a very special phase, which is called the base polytope. And the base polytope is nothing else than one particular phase. So in higher dimensions, this will actually be a polytope, which corresponds to the last constraint being tight. So that means everything in the base polytope, always, all the vectors always sum up to f of v. And that base polytope is the thing that was showing up in our Lovasz extension. And so just in pictures, in 3D, it looks like this. And in 4D, it's hard to draw, so I stopped here. So this is what it looks like. So why is this so special? It's defined for every submodular function. But now let's think about this. What I said was that my Lovasz extension is actually defined like this. So my Lovasz extension, if I had just shown you this, to compute this, you need to solve a linear optimization problem, which is fine, but an optimization problem with an exponential number of constraints, because I have a constraint for each subset of my ground set. And in general, like having a polytope that has an exponential number of constraints is very, very hard to deal with. And it's not so easy to optimize over. It can be very, very hard. So on the other hand, I showed you that actually this Lovasz extension, I could compute it pretty easily. I was just doing my decomposition of the vector, and it was pretty fast, and it was not hard at all. So in fact, that's a very amazing thing. And it was shown by Edmonds in 1970 that essentially for all of these base polytopes, you can always do a linear optimization in n log n time, which is pretty amazing given that I have an exponential number of constraints. And in fact, these polytopes, they are like so-called matroid polytopes, and it's pretty much an if and only if you can do some kind of, which is called the greedy optimization over the polytope, then they have some structure like this. So how did Edmonds define this optimization, linear optimization over that polytope? He called it there it's called the greedy algorithm, and it goes as follows: that I want to maximize this, so I sort my vector x, and then I get a chain of sets where I take first the maximal component, the index of the maximal value, then the second one, and so on and so on. And then I compute my maximizing vector y by simply taking differences of evaluations of f. So why is this called a greedy algorithm? It essentially says I take the maximum value of x, I go as far as possible on that maximal coordinate to be feasible. So here I have to go to the left actually to satisfy my constraint that the first coordinate should be smaller than -1. Then I look at the second coordinate, I satisfy the constraint, go as far as I can, and so on and so on. Now this thing that I get out from here is actually basically the same as what I showed you before. So it gives me this chain of sets, which I can get by thresholding x, and these are also called the level sets, and we will encounter them again and again. That's basically this chain of sets. Now, I showed you this algorithm essentially because it gives you an explicit formulation of how to compute the maximizing y. And the maximizing y is the subgradient of that non-smooth Lovasz extension at the point x. And if we want to do optimization, it's important that we can compute gradients, or in that case subgradients, because it's a non-smooth function. So here's how you do it, and you can do this in n log n time because all you need to do is sort the vector x. That's all, and then you evaluate the function f n times, and that's it. So far so good. Let's just sit back a little bit and see where are we right now. So what we've done so far is we've seen that we have our submodular function, which has these polytopes assigned to it, like the submodular polyhedron and the base polytope. And these polytopes give us the convex extension, essentially, which is easily computable, and also we can compute subgradients of this thing. So that looks very nice for optimization. So in summary, we took our set optimization problem, we changed it into this binary problem, and we defined a relaxation. And now I showed you that this relaxation actually has some nice properties. And well, now let's just solve this problem instead of this one and hope for the best. So there's an even nicer fact is that, in fact, this relaxation is exact and tight. That means I can, in fact, solve that right-hand side convex optimization problem, and I will get the optimal solution for my combinatorial or discrete optimization problem. And this result showed essentially that you can do submodular minimization in polynomial time. That time using the ellipsoid algorithm, which was not the most practical of things, but it's doable in polynomial time. So let's hence look maybe at some methods of actually solving this problem. And you've already seen in the previous lectures how you could possibly solve such a problem, which is slightly easier to implement. So one of them is the subgradient method, and there's another class of algorithms which are combinatorial, which solve the dual of this problem. So let's just go through the ideas of these algorithms to see how you can actually finish solving this problem. So the first one is a subgradient method, and I think you've just seen this in previous lectures. It works as follows, that I start with some feasible solution, maybe zero, all zeros vector, and then in each step I find a subgradient of my function at the current point, and then I go into the direction of the subgradient. So I'm constrained to being in 0, 1, so I'm constrained to sit in this cube. So I take a direction of a subgradient, and then I'll have to project back to the feasible set, which in this case the cube is pretty easy. So how do I get the subgradient? We know it's the Edmonds greedy algorithm. We know how to get a subgradient for the Lovasz extension. So we can do that in n log n time. And the projection is pretty easy. So it's really, this should be a minus here. It's really just, just a truncation. So it's pretty simple, and then we project back, and that's it. So we iterate this, and eventually it will solve our convex optimization problem. So that's one method to solve it. What's the convergence rate of this? So I think you've also learned about this, that essentially you get a root t convergence rate for this problem. That means that after t iterations, the error bound that I can get compared to the optimal solution is of this thing. So now you have some constants occurring in this thing that you usually have. One is the Lipschitz constant, and the other one is the diameter of the feasible set, which is in this case root n. So now we know like how many iterations we need to do to get within a certain range of the optimum. And since this is a discrete problem, you can actually solve this also in finite amount of time. So we have one method now to solve it. Historically, there has been another class of algorithms which has been very impactful for this particular problem. So I just want to show you the idea of what they do. What they do is they do not solve actually this problem, they solve the dual of this problem. So how can I get the dual? I think you've also talked about convex duality, so let's try to apply it. So we have our Lovasz extension problem. We can write our Lovasz extension also as just maximizing over the polytope as we saw. So I can equivalently write it like this. Now I can swap the min and the max, and you can actually do it in this case. So I just swap these two things, and that's pretty much it. So now if I think about it, if I just look at this particular problem, I can in fact get a closed form of x. Basically, if a coordinate of y is negative, I will set x to 1. If a coordinate of y is positive, I'll set it to 0 because I want to minimize, and that's it. So I know what is x, and hence I can just rewrite this problem as if x is 1 at the negative coordinates and 0 at the others, what I get out is this problem. It's the same, just putting in the x, the optimizing x. So this is the dual problem. The dual problem is an optimization problem over the base polytope. So now our feasible region is this base polytope, and it's a concave maximization problem. A non-smooth one, but it's concave, so we can solve it. Now, I also wrote down some optimality conditions. The only one that's really important here right now is this one. What this tells me is that if I solve the dual problem, I get the optimal set by just taking everything that has a negative coordinate. So the elements of my vector corresponds to elements in my ground set, so I take everything that has a negative entry in it, and that's it. Or I solve the primal and I take everything that is a positive entry. So that's pretty much it. So it's very easy to get the rounding in this thing. Okay, so how could we solve the dual problem? And there's a class of combinatorial algorithms that solve the dual problem. And the idea is as follows, that I look at my vector. Here, this is my current vector y. And what I want is I want to maximize the sum of all the negative coordinates. So essentially, I want to remove all the minuses in my vector. So here I just put like pluses and minuses for positive and negative. So I basically have to move, like, want to eliminate this, but I'm not completely free because I have the constraint that my vector y lives in the base polytope. And as you knew, the base polytope has this constraint on vector y has to sum up to a certain value and so on. So essentially, if I would make this more positive, I have to make something else more negative, and I have to keep all the constraints. And that's essentially the challenge in this problem, is to remain feasible, to remain in my polytope. So I have to make this positive by making something else more negative, and I have to know what I can change. So the way you do this is you set up something like a flow problem. So you have maybe seen this from max flow, to basically shift negative mass to other coordinates. But you have to control that you can actually do it. So the techniques are pretty much like that, and that gives you combinatorial flow algorithms essentially to solve that problem. These are somewhat more challenging to implement, so I'll not show you exactly how they work, just give you the basic idea. So this is basically then the picture of some of the optimization methods for solving submodular minimization. We already saw, like, basically the first polynomial time result was just using the ellipsoid method with the Lovasz extension. Then the next problem that people posed was essentially, well, this is very unintuitive and not very insightful from using the structure of the function itself. So the big question that time was like, find me a combinatorial algorithm to solve this problem, which is strongly polynomial type. And this was solved in about 2000. And after that, there has been like a line of work improving on these algorithms and making them faster. And then there are convex optimization methods that you could use, because other than the ellipsoid method here, because as we saw, we have this primal convex optimization problem. We can solve it. And I showed you one method to do so. Now there's another class of algorithms that solves a slightly different problem, which the fact that you can actually use these algorithms also relies on submodularities and very special to this structure. So we see that actually the structure of submodularity, which seems pretty simple, like this diminishing returns thing, actually gives us a lot of algorithmic power in terms of using convexity and using different types of formulations. So let me just show you an alternative way of solving this problem. And that goes as follows. So we started out with a relaxation where we optimize over the hypercube, just the Lovasz extension. Let's try to do something else, that we remove the constraint and instead we add a squared norm to this, which is now also the prox operator of this Lovasz extension that you might have seen in previous lectures. So what about this problem? Why am I writing this thing down? It seemingly, obviously, the optimal solution to this problem is very different to the optimal solution from the previous one, just minimizing the Lovasz extension. And in fact, this would work with not the half here, but any other kind of coefficient too. So obviously, the solution is different. So why would I even want to solve this problem? And the reason why you would want to solve this problem is that this problem essentially solves more than just the submodular minimization problem. It solves the complete parametric version of this problem by as of the following form, that I could say I minimize f of s plus alpha times the cardinality of s for any kind of alpha. Now what would this do? If alpha is minus infinity, I would take the full set. If alpha is plus infinity, I would take the empty set. And in between, I would do something in between. So let's just look at this a bit more carefully. Let's just say let S alpha be the largest minimizer of this thing. So largest, I just say because there could be more than one. And then what you can show, and that's essentially the key thing, is that if I take two of these parameters, alpha and beta. If alpha is smaller than beta, then S alpha is larger than S beta, and in fact is a superset of S beta. So what this means is that as I take my alpha and I go from minus infinity to plus infinity and I go through all possible values, what I get is essentially at most n different optimal sets for different alphas, and they are all nested. And that's very special, so I get like a nested sequence of sets as I change alpha. And I can now encode this nested sequence in a vector. We've already talked a lot about level sets, etc. It's essentially the same idea that I have my ground set of elements and I have these nested sets, and I can encode them in a vector such that if I threshold at a particular alpha, so I take all the elements that have an entry larger than alpha, I get the optimal solution for that particular alpha. And since they are nested, I can encode all of this in a single vector. And that vector is the optimal solution to this problem. Hence, that's why this works. Now, if I want to do submodular minimization, I think in the end, all I care about is alpha equals 0, so I threshold at 0. But now, if I wanted, I could use other values as well. So solving this problem actually gives me more information. But we'll see that solving this problem also gives me different algorithms to solve it, so it might be beneficial just for that reason. So overall, what the picture is as follows that I take this proximal formulation. Now what I solve is actually not exactly this, but I solve the dual of this. Getting the dual for this problem is pretty similar to the dual formulation that I showed you for the non-smooth version. What you get out is the following problem. Find the vector of the smallest length or the smallest norm in the base polytope. So now I have a smooth optimization problem over the base polytope, finding the vector with the smallest norm. That's the dual to the proximal problem, and if I solve the dual problem, getting the primal optimal solution is very easy. I just swap the signs and vice versa. And this problem is maybe easier to solve than the other one. And we saw this is the same as the parametric problem. So we essentially get three problems that are equivalent, and solving one solves the others. I argued you can go this direction. You can actually also go the other direction. If you have a fast combinatorial algorithm for solving this problem, you can solve these as well by doing some divide and conquer approach. So these are really equivalent. Now what does this mean for solving our submodular minimization problem? Let's just recap this a bit. We have the proximal problem. We will actually solve the dual problem. The dual problem is the problem of finding the vector of smallest length in the base polytope. So in picture, it looks like this. So in 2D here, in that particular case, this is the vector that's closest to 0. It's the same as projecting 0 onto the base polytope. In that case, this was our example from before. The vector has coordinates -1 and 1. And what I said was you threshold, and in that case, you take, again, all the negative components of y, and that's your solution that you take. Because y and x are like plus and minus equivalent. So that's the algorithm. We solve the dual problem, and then we take our vector y, and we take all the negative components of that, and that's our optimal set. And if we look at the function here of this toy problem, that's actually true. The element with a negative coordinate is the optimal set in that case, minimizing the function. Okay, so how do we actually solve this problem? I claimed it's easier to solve, or it's nice to solve, but let's actually look at it. So what I already indicated before is that we have to basically convex optimization over a constrained convex set. But the convex set is slightly more complex because it has exponentially many constraints, as we know. So testing membership in this thing is hard. So testing whether a vector lies inside or outside is not so easy because I cannot go through all the constraints and see whether they are satisfied. So that's maybe not such a good approach. Equally, projecting onto that polytope is pretty much the problem we are trying to solve. So that's not a good subroutine for optimization. So anything like a projected gradient or so would be not so great. But the only thing that we know we can do is a linear optimization over that polytope. So that's the same way as we actually computed the subgradient and did computation of the Lovasz extension. So we know how to do that. That's the key. So what does there is a class of algorithms, and I think you have also talked about that, that only needs linear optimization over a complex polytope. So if you have a subroutine doing this, you can do that. This is called the conditional gradient of Rank-Wolf algorithm. There's faster versions of this, which are active set methods. They work much faster in practice. I will, for the moment, focus on the simpler, just conditional gradient algorithm. So how does that work? Well, it works as follows. Here I just wrote it in a generic form. We minimize a convex function h of y subject to y living in a polytope. So here P is the base polytope. And in each step, we do the following. So here's a picture. The color in the end is the objective function. So the minimum, unconstrained minimum of my objective function is here. Blue is low and yellow is high. So I just have the squared norm. I have a current feasible point y. So one thing is that I have to start with a feasible point. But I know how to do this linear optimization over my polytope, and it'll always give me a vector, a vertex of the polytope, so I can always find some point inside, which is a vertex. So I'll start there. And then I compute a gradient of my function. Gradient of the squared norm is easy to compute, so we can do that. And now what I do is I don't do a step in the direction of the gradient directly, because I might step out of my polytope and I can never test that. Instead, what I do is I find a feasible direction. Essentially, I find a direction which is best aligned with my gradient, but it goes to a vertex. So I do a linear optimization over the polytope with a gradient as the cost function that gives me some direction which is most aligned with my gradient. It'll end in a vertex. And now, since it ends in a vertex, I can just know if I go between my point and the vertex, I'm fine. I'll stay inside my set. So that's it. So I'll do that, and I iterate. Case. So I find my gradient, I find some point, and so on and so on. So I can optimize. Of course, there are some other questions like what's actually my step size gamma and how many iterations should I go. And there's actually a number of different ways of deciding the step size. The easiest one is just to take something like 1 over t. You can do re-optimization as well, which comes closer to the active set methods. It requires a bit more memory and is a bit more costly. So how many iterations should I do? Like, can I get a convergence bound for this algorithm? And more notably, what I'm actually interested in is the rounded version of this thing. So I'm actually not so much interested in the convergence rate of this thing, but the actual rounded solution. But let's start with this thing. And to proceed to the very end, what we'll do is we look at the duality gap instead of just the difference of the function values here. So just as a reminder, I have my primal and dual problem. We have strong duality here, so at the optimum of these, they two agree. So what I can now use as sort of to measure convergence is the difference between the primal and dual objective values. And I can, in fact, get a bound on the duality gap here, which depends, again, on some constants, which are like the diameter and the Lipschitz constant of the thing, divided by t. So that's the convergence rate after t iterations. So how do I now get a convergence rate for the discrete problem? Here's what we did. We have to go back now to our rounded solution. And in fact, it's possible to go from if I have a convergence rate which refers to the duality gap of my relaxed problem, I can go back and get a convergence rate for the duality gap of the actual discrete problem that I started with. So I'll just state that result. I'll not prove it for you. But essentially what it says is if the gap is on the order epsilon, then this thing will be on root 2n epsilon prime. So I can get a direct correspondence. And of course, the duality gap is a bound on the actual gap to the true objective value. Now here, I do the rounding by just taking the best level set of my current vector. So that's basically, again, the level set. So what this shows you is just that you can get a complete analysis of the convex optimization that's behind all of it, of the actual algorithm down to the end of a convergence rate for the discrete problem. So let me just give you some kind of summary of the different optimization formulations that we've just gone through. So one was that we started out with the non-smooth relaxation. We have the dual or the primal that we can solve, and alternatively we can solve the proximal problem or the dual of the proximal problem, which is just a projection onto the base polytope. There are different algorithms for solving these. In practice, the fastest is usually to solve this problem and to use the Fujishige-Wolf algorithm, which is faster than the Frank-Wolf algorithm that I showed you. It's a variant that uses essentially an active set, but it uses the same kind of generating a vertex to go in that direction and add to the active set. There are other alternative algorithms if you have special cases of submodular functions. I didn't really talk about these. I showed you in the beginning that graph cuts are a submodular function. Of course, you can have a specialized algorithm for solving a minimum cut problem. You don't need to go through this. But if you have a general submodular function, these don't work any longer. You can use any of these methods. Now, there's another thing that if you actually think about the algorithms that I just showed you, they are actually not as different as they might appear in the beginning. There are connections between subgradient methods and these conditional gradients as follows. Let's just parallel them a little bit, and I'll show you the connections between the two. The subgradient method worked by just computing a subgradient and then going in the direction of the subgradient. So now if we can apply the same thing to this problem. The subgradient is again the argmax over the base polytope given by the Lovasz extension, and then we just go in this direction. If we do conditional gradient of Frank-Wolf, what we do is we are operating in the dual. We get a vertex which is most aligned with the gradient at the current point yt. So we solve a minimization problem over the base polytope, and we go in the direction of that vertex. Now, if you look at this and you look at this, the direction in which we go is actually not all too different. If you look at this problem, now if you think about that, the primal and dual solutions actually are just one is the negative of the other. If you use this connection, then minimizing for y or maximizing over x, which is minus y, is the same. So the vectors, if x is minus y, then these are actually the same directions. So you can, in fact, get a direct correspondence between these two methods in the primal and dual. They're solving the same. There's a direct correspondence between the two. So you see, actually, also if you write it in the correct way, the iterations are very similar. So in summary, we saw we have the convex Lovasz extension, which gave us a lot of different duality and optimization results. What is this useful for? So first of all, we get interesting algorithms out of this, like lots of different, basically all your convex optimization toolbox, you can try it out on this. Try different algorithms. The second thing is that the Lovasz extension and these different formulations give us additional applications. So one of them is for structured sparsity. The other is for deriving parallel algorithms. You can do more with this. So you can, in fact, what I showed you was you have these probabilistic models. You can get the mode of the distribution, which is just map inference. You can do more. You can get approximate marginals as well, using formulations like the min-norm formulation. I don't have time to go through this, but I'll put all these references up, so if you're interested, you can look at the paper. So let's look at some additional applications that just fall out of these connections to convexity. The first one is, again, the sparse reconstruction framework. So what we have here is that we are observing a noisy signal, y, which we know has a true underlying signal x, where x can be written as a sparse combination of basis vectors of some sort. So this could be images, this could be all sorts of other kinds of bases or dictionaries, so dictionary reconstruction and so on is a special case of this. In particular, what we have is that we often have an overcomplete dictionary. That means the dimension, the number of vectors here is much larger than the actual number of observations. So this problem is ill-defined. So the way to solve this, the only way we can actually solve this is by knowing some additional structure. For example, that what actually counts is actually just a few of these are used. So a few of the components of X are actually non-zero. Similar things happen in regression problem where now the matrix M is actually the data and then X will correspond to some regression coefficients. But it's pretty much the same setup. Here we're just trying to minimize then the squared norm. So it has many different applications, and I think you've heard about it also. I showed you in the beginning, this is basically a subset selection problem. I'm trying to select the coordinates where X is non-zero. So I'd like to actually put this into a real learning framework. What I do is I don't only have the squared error, I put a regularizer. And this regularizer tells me, implements my assumption that X is actually sparse. What I would ideally like is to put basically just say, well, X is sparse, so I want a penalty on the number of non-zeros in X. The more non-zeros I have, the worse it is. The more penalty I'll get, so I'll bias myself to have sparse solutions. So I could do this by just putting a cardinality on what's called the support of X is just the entries, non-zero entries. That's, of course, not so easy from an optimization perspective. So a common approach to this is just to take the L1 norm instead of the L0 norm. The L0 norm would correspond to the cardinality. That's a common framework to just then take the L1 instead. And L1 also works to get sparse solutions here under certain conditions. Now in the real world, what often happens is that the sparsity, you actually have more knowledge than just the vector is sparse. So for example, what we are actually having is genetic data, and I know that the components that count, like also for classification, is not arbitrary entries in my vectors, which now corresponds to different regions in the DNA. It's actually consecutive entries because of the way things are read out. So I have some activator, and then things are being read out in a sequential frame. So what I'm actually preferring in this case is not arbitrary sparse patterns, but something that's consecutive non-zeros, and then the rest is zero. Or in image reconstruction, I could know that my basis here is actually a wavelet basis. Now, if this is a wavelet basis, I can also arrange the basis vectors on a tree. So one top thing looks at the entire image, and then I get smaller and smaller and smaller. So in that case, it's more likely that the true activation pattern actually corresponds to a subtree in the tree rather than to an arbitrary set of nodes in that tree. So could we have regularizers that actually incorporate this kind of assumptions? So, well, as I said, we came from a set function. We could express this maybe by a set function on the sparsity patterns because it's nothing else than subset selection and all the way we talked about subset selection problems. So could we have a set function that expresses the preferences for trees, for example? So in fact, we can, and here's an example. Let's just say that the following, all of my variables correspond, each variable corresponds to a node in the tree, and my set function is the number of nodes if I include all the ancestors of my node. So I have to include for each node the way to the root of the tree. In this case, there's only one additional node to include, and then I just count the number of nodes here. So here it's just 4. So for the subtree, it's pretty small. For another set of non-zero entries, which is the red 3 here, so notably these are 3 and these are 3. So number of nodes that I'm picking is the same. But in this case, I have to pick a lot more ancestors because they are much more spread out in my tree. So in this case, the cost is 6, whereas in this case, the cost is 4. So that's a simple example that I can implement a preference for a certain structure, and you can do this with other structures as well. Now I have a set function. Could I use this somehow to create a regularizer that implements this kind of assumption on my patterns? So I could just follow the same framework as here. So beforehand, I just penalized cardinality. I could penalize something else. Now I know that the previous function is a submodular function, and for any kind of submodular function, I could do the same. Instead of cardinality, I could put my set function up here. Let's just try it. Now, though, what would this step correspond to? Here we went from the set function to something that's called the convex envelope. The convex envelope is nothing else than the largest or closest convex function to this discrete function. In this case, the convex envelope, we know it already, it's the Lovasz extension. So I can do the same thing, and in that case, I just take the Lovasz extension and take the absolute values of x. And I can use this to get a structured sparsifier. There are two interesting points to this. The first thing is that this Lovasz extension actually defines a norm. So what we have here is an L1 norm. Norms are usually very nice to have. They have nice properties. What I leave to show you as an exercise is that this function also defines a norm. Always, if this is a submodular function. The second thing is, how do we actually now optimize this? The optimization of this, if you do a proximal gradient algorithm, the proximal step is nothing else than solving the min-norm problem. If you remember, we have f of x plus the squared norm. The squared norm could be some other stuff as well, which looks like this. That's it. So you know how to actually solve this problem with the methods that we just talked about. So yeah, so your submodular function, I already said that corresponds to a norm. Very simple examples are not only the tree function, so the cardinality function. You can get the infinity norm out. We've already seen this. You can get something like group norms. You can get overlapping group norms and so on. So Z functions are pretty general. These are just some very simple examples that correspond to other norms that you might have seen. So this just gives an additional application of defining norms from submodular functions that we could use for regularizers and other things. There's another interesting application of the framework that I just showed you. Not directly the algorithms, but the analogies of the different problems. And that is for defining parallel algorithms. So in many cases, my submodular function is actually not arbitrary, but it corresponds to a sum of submodular functions. So notable cases are, for example, these energy minimization problems, where often I showed you the simplest case of these pairwise pixels. There's other things that correspond to patches of pixels that should take the same label and so on. In many cases, these are submodular functions. And they are much simpler because either they correspond to functions that have a small support, or they correspond to functions that have a very simple form. So many cases, this actually corresponds to a sum of functions, and each of the FIs by themselves is super simple. I have a specialized subroutine to solve it or so. So I would like to exploit this structure. There's various ways of doing this. Let me just show you the results for using convex relaxations and the analogies that I just showed you. So we can do the same thing. We start out with our set function and we do a relaxation. So far it's just the same as we had. We take the Lovasz extension. Now the Lovasz extension of a set of functions is just the sum of Lovasz extensions of the small functions. Now what I have is I have an optimization problem that optimizes a sum of convex functions, each of the FIs here. And that's nice. There's a lot of different, there's different methods for addressing these problems, exploiting that I have a sum of convex functions. Mostly the idea is that I take this problem, I take the dual. The dual looks like a decomposed problem where I have lots of different functions and they are independent. So I have if these are k functions, I'll have k different independent optimization problems and a coupling variable, similar as we saw in the previous lecture. So I can use methods for solving that. What I can also do is I can do the same trick and use the proximal problem instead. And I again take the dual, I again do the decomposition. And I'll not go with you through the derivation, but essentially the idea is that the duals of these problems are very different. The dual of this problem is a non-smooth problem as before. The dual of this problem is a projection problem, and it's essentially the problem of finding the two closest points between a hyperplane and a big polytope. But solving this problem of finding the two closest points is a very geometric problem, and there's nice algorithms for that that are projection type algorithms that don't even need any kind of step size setting or so. So it's kind of easier even to implement this. And what does it look like in results? So here's just convergence rates for the non-smooth relaxation and the proximal problem. And here's a bunch of algorithms that solve this relaxation. We'll not talk about all the details. And here's a bunch of algorithms that solve this one. And these are usually much faster than these in practice. So you see, you don't only get the advantage from the Frank-Wolf and Fujishige-Wolf algorithms as before, even if you just want to do a decomposition, and now these are in the dual, these are parallelizable algorithms. You get faster parallel algorithms by using the structure of submodularity and the different analogies that we've seen. So it's useful in many different ways. Yeah, so we get this. So with this, it's 12:30. Let me just wrap up. What we've seen is that submodular functions occur in lots of different problems in machine learning, and also I showed several applications from computer vision. Submodularity, even though it looks like a very simple and innocent structure, just diminishing returns, it actually has a lot of different wide-ranging applications via the connections to convex functions. So what we saw is you get these very nice polytopes, and the key fact is that these polytopes, you can do a linear optimization in n log n time. It's just the sorting, essentially. That gives us this Lovasz extension, which is convex, which is easy to compute. And we can do convex optimization. Moreover, we get lots of different additional applications from using the convexity framework. So with this, I'll let you go for lunch. And after lunch, we'll talk a little bit about constrained optimization and maximizing submodular functions.